In this next example, we consider slicing a shape again, but using a different axis of rotation. So we're going to stick with our y equals negative x graph, so the exponential decay graph, but this time we're going to spin it around the y-axis. So imagine this area here being spun in 3 dimensions to obtain a cone again, but it'll be a different cone than the one we saw in the previous example. It'll have a peak at the top here and then spin out and flare out this way. The question then becomes, if we want to find the volume of this shape, how should we slice it up to develop an integral? Now, what we could try to do is replicate what we did in the previous example, which is slice in the direction perpendicular to the x-axis, so slice this way. But if you look at what that would be in this shape here, that would be slices along this direction, and the shapes would actually be quite complicated. There's maybe little bell curves or something like that. It certainly would not be a simple shape. So in this particular example, would this be a good way to cut out the shape? No, because the shapes, the slices shapes, are complex. In contrast, in startling contrast, if we cut instead, let's remove those, if we cut instead into horizontal slices, well, that would translate into circles. Because of the way this was generated spinning around the y-axis, when we cut perpendicular to that axis, we're going to get circular shapes. So if we cut this way, we're going to get thin cylinders. And this is a good way to slice the shape. Because we can find the volume of those thin cylinders in a straightforward way, whereas finding the volume of little thin slices of exponential curve like that, that is not quite so straightforward. So we won't do that. All right. So what do we do next? We take a look again at our cross-section. We imagine our thin slices and remember where the boundaries of those slices come from. In fact, let's make that a little more precise. We would take a thin cylinder and it would go around like this because we've spun it. And what we're interested in is the radius to get the area of the circle so that we can get the volume with the thickness. What thickness will we use? Well, delta y makes sense because we're talking about a small distance in the y direction. Okay, so how do we get a volume of that slice? Well, same as before. The slice is going to look like a cylinder. If we look at it on end, it's going to be a thin cylinder like this. We need to know the radius. So it'll be the area of the circle times the thickness, and the area will be pi times its radius squared. The thickness will be delta y. Now, in this particular scenario, we think of the cylinder being bounded by the curve. The curve here is y equals e to the negative x. The radius this time is an x distance. Here's the center. The x coordinate on this curve is exactly the radius we want. So pi x squared is in fact the area of the circle. We're going to multiply by the thickness delta y. But if we're going to be using delta y, then we have to write x in terms of y. And how do we do that? Well, this x coordinate and the y coordinate are related through y equals e to the negative x. The challenge is we need x equal to something because we want to replace the x's with y's. So how do we resolve that? Well, we solve for x. We're going to take the ln of both sides. If we take the ln of e to the negative x, we just get negative x back, or negative ln of y is x. So we needed x. We use the relationship that relates x and y on that boundary. That brings us back down to here, and then we can plug that x in and get pi negative ln of y all squared delta y. That's a radius squared times pi, area of a circle, times delta y, the thickness. So again, try to look for patterns as we go through this. In particular, using the formula for the boundary in some way is crucial to finding the volume of a generic slice. Here we have to use that curve to get to the radius, which is involved with the area of the circle. That again is the hardest part. Writing down an integral that represents the total volume is straightforward because we just want to add up all the slices from the top to the bottom. So we copy down our integral here, with the only change being the delta y converted to a dy. And then we ask ourselves, where do we start slicing and where do we stop slicing? That information was given on the last page. We're going to slice only between y equals 0.1 and y equals 1. So there's a little boundary area we don't include. So 0.1 up to 1. 0.1 and y equals 1. And that becomes our integration challenge. So we will notice very quickly that this integral is a little more complex than some of the earlier ones we've had. So let's take a look at how we'd evaluate it. We have the total volume is equal to pi out front, 0.1 to 1 of negative ln of y squared dy. And notice that the negative here doesn't matter because we're going to square it. So we can write that as pi 0.1 to 1 of ln of y all squared. Now, what kind of integration technique do we need here? This does not look like a substitution. If I choose a substitution with ln y, we'll have the derivative show up, 1 over y. That's not going to make life any easier. This would be one of those classic integration by parts examples, because all we can do is differentiate the ln of y squared. So in this case, we do have a fairly challenging integral. We have the u and the dv we need to define. We know how to differentiate ln, or ln of y squared. So we'll put that as our u. The dv will be just the dy part left over. The steps are we integrate this, we take a y derivative, because that's our variable now, and we're going to get 2 ln of y times the derivative of the inside, which is 1 over y. When we integrate the v and y, we're going to get just y. The integration by parts formula says you take u times v and then v du. So we'll have pi times u times v, that's y ln of y all squared, minus y times, minus the integral of y ln of y, forgot to do y here, y times 2 ln of y 1 over y dy. This is between 0.1 and 1, so is this. And did that help? Well, it helped a little bit. We can get rid of our y's here, they cancel. Now we're left with the integral of ln y with a 2. I think we can work with that. Let's simplify it next. We've got pi times y ln of y squared 1 and 0.1 minus the 2 can come out, and the integral of ln of y dy. Now how do we tackle that integral? Well, in fact, this is one of the first integration by parts examples we did, at least one of the more interesting ones. We can do it by parts again with another application, and this time with u equal to ln of y, dv equal to dy again. Once we pick that, the derivative is 1 over y dy. The integral is y, and we have our mix. The integral here can be written as u times v minus the integral of v du. So we extend this another step, and what do we get? We get pi y ln of y squared. Let's be a little more precise with the brackets there. And we're going to get some more stuff next. So minus 2 ln y, 2y ln y, all of that between 1 and 0.1. And then we still have the 2 here, so minus 2 times the integral of, oh wait, we have a minus, and we'd subtract the integral, so it's actually plus the integral, 0.1 to 1 of y times 1 over y dy, and we're done. Almost done. Oh, phew, those cancel. That and that cancel, and we just get 1. So we have a complicated expression plus 2 times the integral of dy. We'll continue that on the next page. That's our expression rewritten, and the last integral to evaluate is simply the integral of 1, which will give us y. So pi out front. Y ln of y all squared minus 2y ln of y plus 2y. And we see a nice pattern here. We see changing signs, and we have ln of y squared, ln of y. Each time we did integration by parts, we removed 1 ln of y. And all of that between 0.1 and 1. Okay. Last step, plug in the limits of integration and see what we get. So pi times 1 ln of 1 squared minus 2 times 1 ln of 1 plus 2 times 1. That minus 0 ln of 1, oh, 0.1. It doesn't cancel out quite that easily. Not this time anyway. Minus 2 times 0.1 times ln of 0.1 plus 2 times 0.1. Now, other things do cancel nicely because ln of 1 is 0, ln of 1 is 0. So we end up with pi times 2 minus 0.1 ln of 0.1 squared, double negative, plus 0.2 ln of 0.1 plus 0.2, oops, negative again, negative and positive. That'll be negative. And if we work all that out, we end up with approximately 0.8093 cubic units. And so the volume of that particular shape is approximately 0.8093 cubic units. So in this particular example, the integration step was fairly complicated, integration by parts twice, but that's why we have the techniques. But again, more importantly overall is the derivation of the integration in the first place, because that's the kind of thing that computers have a hard time doing, but human beings can do quite easily, is with a systematic approach decide how you're going to slice this object up, determine the volume of a representative slice, and then find the sum simply by adding an integral out front and converting the delta y to a dy.